Hello and welcome. My name is Alan, and today we are back with more ideas and opinions of Albert Einstein. We're going to read part three of this long piece we've been reading. This part's actually not that long at all. We're looking at a couple and a little over 3 pages, so. But stick with me. Let's jump right into this. Part three, the field concept. In explaining optical and electrical phenomena, Newton's mechanics has been far less successful than it's been in the fields cited above. It is true that Newton tried to reduce light in the motion of material points in his corpuscular theory of light. Later on, however, as the phenomena of polarization, diffraction, and interference of light forced upon this theory more and more unnatural modifications, Huygens' undulatory theory of light prevailed. Probably this theory owes its origin essentially to the phenomena of crystal optics and to the theory of sound, which was then already elaborated to a certain degree. It must be admitted that Huygens' theory also was based on the first instance upon classical mechanics, the all penetrating power, the all penetrating ether first instance upon classical mechanics. The sorry, the all penetrating ether had to be assumed as the carrier of the waves, but no known phenomena suggested the way in which the ether was built up from material points. One could never get a clear picture of the internal forces governing the ether, nor of the forces acting between the ether and the ponderable matter. The foundations between the ether and the ponderable matter. Sorry, between the ether and the ponderable matter. The foundation of this theory remain, therefore, eternally in the dark. The true basis was a partial differential equation, the reduction of which to mechanical elements remained always problematic, for the theoretical conception of electrical and magnetic phenomena, once introduced again, masses of a special kind, and between these masses one assumed the existence of forces acting at a distance, similar to Newton's gravitational forces. This special kind of matter, however, appeared to be lacking in the fundamental property of inertia, and the forces acting between these masses and the ponderable matter remained obscure. To these difficulties, there had to be added the polar character of these kinds of matter, which did not fit into the scheme of classical mechanics. The basis of this theory became still more unsatisfactory when electrodynamic phenomena became known, notwithstanding the fact that these phenomena brought the physicists to the explanation of magnetic phenomena through the electrodynamic phenomena, and in this way made the assumption of the magnetic masses superfluous. This progress had indeed to be paid for the increasing the complexity of the forces of interaction which had to be assumed as existing between electrical masses in motion. The escape from this unsatisfactory situation by the electric field theory of Faraday and Maxwell represents probably the most profound transformation of the foundation of physics since Newton's time. Again, it has been a step in the right a step in the direction of the constructive speculation which has increased the distance between the foundation of the theory and sense experiences. The existence of the field manifests itself, indeed, only when electrically charged bodies are introduced into it. The differential equations of Maxwell connect the spatial and temporal differential coefficients of the electric and magnetic fields. The electric masses are nothing more than places of non-vanishing divergence of the electric field. Light waves appear as undulatory electromagnetic field processes in space. To be sure, Maxwell still tried to interpret his field theory mechanically by means of mechanical ether models, but these attempts receded gradually to the background following the representation of the theory purged of any unnecessary trimmings by Heinrich Hertz, so that in this theory the field finally took the fundamental position which had been occupied in Newton's mechanics by the material points. Primarily, however, this applied only for the electromagnetic fields in empty space. In its initial stage, the theory was yet quite unsatisfactory for the interior of matter because there two electric vectors had to be introduced, which were connected by relations dependent on the nature of the medium, these relations being inaccessible to the theoretical analysis. An analogous situation rose in connection with the magnetic field, as well as in relation between electric current density and the field. Here, H.A. Lorentz found a way which showed at the same time the way to an electrodynamic theory of bodies in motion, a theory which was more or less free from arbitrary assumptions. His theory was built on the following fundamental hypotheses. Everywhere, including the interior of ponderable bodies, the seat of the field is the empty space. The participation of matter in electromagnetic phenomena has its origin only in the fact that the elementary particles of matter carry unalterable electric charges and, on this account, are subject, on the one hand, to the actions of ponderomotive forces, and on the other hand, possess the property of generating a field. The elementary particles obey Newton's law of motion for material points. This is the basis on which H.A. Lorentz obtained his synthesis of Newton's mechanics and Maxwell's field theory. The weakness of this theory lies in the fact that he tried to determine the phenomena by a combination of partial differential equations, Maxwell's field equations for empty space, and total equations, Maxwell's, er, and total differential equations, equations of motion of points, which procedure was obviously unnatural. The inadequacy of this point of view manifested itself in the necessity of assuming finite dimensions for the particles in order to prevent the electromagnetic field existing at their surfaces from becoming infinitely large. The theory failed, however, to give any explanation concerning the tremendous forces which hold the electric charges on the individual particles. H.A. Lorentz accepted these weaknesses of his theory, which were well known to him, in order to explain the phenomena correctly, at least in general outline. Furthermore, there was one consideration which pointed beyond the frame of Lorentz's theory in the environment of an electrically charged body. There is a magnetic field which furnishes an apparent contribution to its inertia, should it not be possible to explain the total inertia of the particles electromagnetically. It is clear that this problem could be worked out satisfactory only if the particles could be interpreted as regular solutions of the electromagnetic partial differential equations. The Maxwell equations and their original form do not, however, allow such a description of particles because their corresponding solutions obtain contain a singularity. Theoretical physicists have tried for a long time, however, to reach the goal by modification of Maxwell's equations. These attempts have, however, not been crowned with success. Thus, it happened that the goal of erecting a pure electromagnetic field theory of matter remained unattained for the time being, although in principle no objection could be raised against the possibility of reaching such a goal. The lack of any systemic method leading to a solution discouraged further attempts in this direction. What appears certain to me, however, is that in the foundations of any consistent field theory, the particle concept must not appear in addition to the field concept. The whole theory must be based solely on the partial differential equations and their singularity-free solutions. So yeah, Einstein talking about uh, the field concept and physics and how it kind of conflicted with a number of other scientists when they tried to resolve the issue or prove the theories themselves. But yeah, that'll be it for this episode. As always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next episode. Until then, later.